This tutorial is about solving ordinary differential equations using Euler's method, and Euler's method is used to solve first order differential equations. And we will be looking at free fall of an object. The problem given to us is a 1 kilogram mass is falling along the y-axis. It might be going up or down in a gravitational field where the gravitational field is pointed downward, so it's minus 9.81. The velocity of the object at time 0 is 5 meters per second, and it was released from an elevation of 50 meters. So the question is, how is this object behaving as it falls down? So if we don't consider any air friction, the rate of change of velocity or the acceleration is equal to the weight of the object. And if we want to implement it using Euler's method, we know that if we know the initial condition, then the next value of the function is the previous value plus a small change, which is slope times the time interval. So if we implement this, we have the initial value of 5 meters per second, and so all future velocities can be computed from the current velocity minus 9.81 delta t. This plus shouldn't be there. And so if we are trying to implement this into the future up to Tn seconds, then the number of steps, which is capital N, can be computed by just looking at the time difference or the overall time interval divided by delta t, and that will give us the number of steps. So let's implement this for the freely falling object. So mass is 1 kilogram and g is minus 9.8. And the initial conditions are that for time 0, the location is 50 meters above the ground, velocity is 5 meters per second, and the x location, we need to give some x location, so this could be any arbitrary value, so I'm setting it to 0. And similarly, we can find the number of steps. So we are going to observe the dynamics up to 20 seconds at 0.1 second interval. So in that case, the number of time steps we get is 200. So in order to hold all the values at all the time intervals or time steps, we need to create arrays of the size 200. So I'm going to use this nan function. Nan means not a number, and the reason we use nan instead of zeros is because we don't want to plot zeros on our plot, and nan will not show on the plot as we are plotting these values. So that's an array of size 200, but it is all not a number, nans. But at the same time, we know that the initial condition, the first nan, is 0 seconds. Okay. So now you will see that the first value is 0. The rest of these values will be filled as we run the Euler's method at each time step. In a similar manner, initial y is 50, and there's an array for y values, and similarly v can also be created with initial value of 5 meters per second. So if you observe v, you can see it's all nans, but the first value is 5 meters per second. So this is what we have created, and we will update all of these other values through an iterative process. And again, we need an x value, so we're just setting it to be 0 for all the range. Okay. Then we start a loop. So we know the first value. We're going to start finding from the second iteration or the second index. So for n is equal to 2, we're going to find Tn, which will be the previous value plus the time step. So of course, if you look at the time interval, it has taken the first time step, which was 0, and then added 0.1 to it. Similarly, the next velocity value is also computed using Euler's method. And if we view now velocities, you can see that the second value has become 4.019 meters per second. And similarly, the location is computed using the velocity. So we know it was moving at 5 meters per second at the beginning of the interval. So 5 times 0.1 is the distance that it has traveled, which is 0.5 meters. So if we run this, you can see that as it was moving with 5 meters per second, it went from 50 to 50.5. And of course, you must be wondering, why is it going upwards? Well, 5 meters per second is a positive number. So it's upward velocity, it's moving upwards. So this way, we find all the values, next step time values, and then we can visualize it. So right here, this is the plot of the location. And so you can see that it is at 50.5 and 0. And I can do a hold on and teach you another command called quiver. Quiver just plots a little arrow. And I'm telling it that plot an arrow at a location 0 and 50.5. And its x direction is 0, but y direction velocity is vn, which I just computed. And this will put an arrow at that location. So you can see it's an upward velocity of 5 meters per second. We are just putting this to show what is the direction and what's the magnitude of the velocity. And then we hold on. Now, as you can see, this plot is very awkwardly shaped. First of all, its x-axis and y-axis are not scaled. So first of all, we set up the axis to go from -100 to 100 in both directions, and now we will be using this plot throughout our animation. And then again, sometimes you can have x-axis and y-axis awkwardly shaped. Let's say your plot looks like this. So this is 200, this is 200, but it's not the same scale. In order to do that, we have a command called axis square, and that ensures that the axis is scaled appropriately in both directions. And then we also can have the grid on, so we can see a little bit better in the visualization. And one last piece, we know this is our ground level. So let's put a line here. Again, we'll have to do a hold on because I turned to hold on because I held off it earlier. And then this line here is just putting a straight line, a green line from along the x-axis direction at y is equal to 0, and hold off. So this plot will be updated every time. And if you observe, I am using a CLF here. Every time I come to this point through the iteration, I'm saying clean up the plot and replot a new location. And that's the end of the loop. So let's run this code and see what happens. So as you can see, it went up a little bit, and then it started moving down, and then it keeps moving through the ground, and it keeps moving downwards. Let's run it to 10 seconds, and let's give it an upward velocity of maybe 7. Let's see what happens. Goes up a little bit, and then it starts coming down, and again it crosses the ground. So in order for us that it doesn't cross the ground, we want it to bounce, we can put a boundary condition for this location. And I have here copy pasted that boundary condition. I will explain it. After we have computed the new time, velocity, and location, we can put a condition here, domain boundary condition. We say if the location becomes negative, that is yn is less than 0, that means we have gone beyond this point, then set it equal to 0 and change the velocity. And I'm saying, if it was an elastic collision, the object at this point will just bounce back upward with exactly the same velocity with which it hit the ground. I'm saying, it may be an inelastic collision, and let's give it 70% of its initial velocity. So we just multiply it with minus 0.7. So we are bouncing it back upwards with the 70% of the velocity, and that kind of takes care of that bouncing part. And now let's run it again and see what happens to it. And you will see that once it reaches the ground, it should bounce back up with exactly the same velocity, or 70% of the velocity, but in the opposite direction. So it won't go back all the way to the top. and you can see how it will keep bouncing back. Let's run it for 20 seconds now, and see how it goes. And so basically you can see that how we can solve a differential equation, but at the same time we can visualize the dynamics of that differential equation. Going back to our original problem, we are trying to understand how is this object behaving into the future given an initial condition and a differential equation that is describing its dynamics.